everyone. So this is FRQ video number 3 out of 3 for Mr. Papako's class. We are going to be going over a free response question and all of its parts. It has 4 parts, I think. Yeah, wait, A, B, C, yeah. Just, it's a long one. This is from the 2019 AP Physics 1 free response questions, and it is number 3. So I'm going to begin by reading out the problem, and then we will go from there. There's a diagram that will kind of help us conceptualize this problem. So I'll start it off. A projectile launcher consists of a spring with an attached plate as shown in figure 1. So spring, plate. When the spring is compressed, the plate can be held in place by a pin at any of 3 positions, A, B, or C. So if we look back at our diagram, those are the positions that are labeled. For example, figure 2 shows a steel sphere placed against the plate, which is held in place by a pin at position C. The sphere is launched upon release of the pin. So in figure 2, we can see that the pin is holding the plate at position C, and the sphere is being launched once it is released. So that's kind of the diagram, the problem. Yeah, okay. First question. It says, a student hypothesizes that the spring constant of the spring inside the launcher has the same value for different compression distances. So before we even get into the first problem, I'm guessing that a lot of you are going to be wondering what a spring constant is. So what a spring constant is it is a number that measures the stiffness or not stiffness of a spring, and it is used in many equations. One of the most important ones, I think, to know is Hooke's law, which is F equals Kx. That's what it looks like. F equals Kx, where F is force, K is the spring constant, and in most equations, K is going to be denoted, or the spring constant is going to be denoted as a K. And X is the displacement that the spring compresses. So if we can imagine a spring being, let's say 50 newtons of force, 50 newtons of force is used to push a spring about 5 meters. In that case, it would be 50 newtons equals K times 5 meters, right? Just plugged in my force and I plugged in my displacement, and I got that K would be 10 Newton meters. So another important thing to remember is that the spring constant value is in Newton meters. And the bigger the spring constant is, the more stiff the spring is. So essentially, if you think about it conceptually, the more force that it takes to push that spring inwards for longer distances, the more stiff that spring is going to be. So I think that's really important to remember, that that's what Hooke's law is. You could also be given the spring constant and the distance and be asked to solve for a force. So that's multiplying how stiff the spring is by how many meters it's displaced. So say the spring constant, I give you a problem gives us K equals 1 Newton meter, and X, the distance that it's compressed, equals 5 meters. Well then, F equals 1 Newton meter times 5 meters, right? And then we can kind of see in that situation, let me make sure I'm pointing to the right one. There it is. F equals 1 Newton over 1 meter times 5 meters, that the meters would cancel and we'd be left with 5 newtons is the amount of force it takes to compress the spring at that distance based off the spring constant. So it's a really valuable thing to understand. And I think it's important before we even start the problem to know what a spring constant is. Also, when it says a student hypothesizes, that means that the student is making an educated query into the relationship between the spring constant and the different compression distances, and the student is going to later on in the problem go through an experiment where they try where they explore that relationship and see how it correlates. So that is another thing I wanted to clarify. So 3A, or the first part of the problem, asks, the student plans to test the hypothesis by launching the sphere using the launcher. So, and then it says, to state a basic physics principle or law the student could use in designing an experiment to test the hypothesis. The hypothesis being that the spring constant has the same value for different compression distances. So the first principle or law that popped into my head that I think would be really useful for this problem is the law of conservation of energy, which essentially states that energy is conserved. Now, what does conserved mean? It means that the energy in the very beginning is the same to the initial energy is equivalent to the final energy. Now, that's not saying that, well, let's talk about what energy is. It is the ability to do work. And let's talk about what work is, because we have to understand that to understand energy. So work is force times displacement. And we'd and the force and the displacement need to be in the same direction for work to be done. So like, say I'm applying a force of 5 newtons on this on the horizontal axis, or say it's on the table, and it's pushing it this way, and it displaces 5 meters, let's say, right? So then how we'd calculate work is 5 newtons was applied, multiplied by 5 meters, and our work would be 25 joules. And work is in the unit joules, which is important to remember. It's just a unit of work. So that work done was me applying that force and multiplying it by the displacement. There's also negative work, which is a term that helps me understand which direction it's pushing. So let's go back to our scenario of me pushing this eraser, applying force and pushing it on the table. Well, there's also the force of friction working against it. So we would multiply friction by the distance that the friction was applicable, which would have been the whole distance. So say our value of friction was 0.1 newtons, and multiply by the distance 5 meters. So we would get 0.5 joules of negative work, right? Because 25 joules being applied, or 25 joules of work being done this way, and the friction was doing 0.5 joules of work in the other direction. So we'd call that negative work. So going back to energy, energy is the ability to do work. And there are two different types of energy that we're going to be discussing. One is potential energy, which is the stored energy of an object, and it's usually based on its position or circumstance in that moment. And that doesn't account for when the energy is in motion. That is what kinetic energy is. So potential energy is the stored energy of an object or system. Kinetic energy is the energy of the object or system in motion. And it's important to remember that these energies can be transferred through one another. But going back to our equation, the idea that energy is conserved, you might be thinking, okay, so the initial kinetic energy is equivalent to the final kinetic energy, and the initial potential energy is equivalent to the final potential energy. But that is not the case. It's the total energy, because energy is being transferred between the potential and kinetic. So a way to write that would be PE1 plus KE1 equals PE2 plus KE2. So all that we can see here is that this total initial energy is equivalent to that total final energy. And I just wanted to note that non-conservative forces come into play, and that is added onto the final energy. So actually, we don't need to talk about that for this example. So let's break down the potential energy and kinetic energy into more cohesive equation. Well, actually, yeah, that will leave the law at that, and then we will go to the next question, because it kind of addresses how to get into the specifics of the experiment. So the next question asks, using the principle or law stated in part I, determine an expression for the spring constant in terms of quantities that can be obtained from measurements made with equipment usually found in a school physics laboratory. So if we think about our expression, or the expressions that I was talking about, PE1 plus KE1 equals PE2 plus KE2. Well, potential energy and kinetic energy can't exactly just be measured. You can't look at an object and say that has this amount of potential energy, but there is a further expanded equation that has values that we can measure with things that we can find in a school laboratory. So if I'm going to read out the equation, and then we'll go through, or I'll explain the sections that go into this equation. So the expanded version, potential energy 1. So there's two types of potential energy that are going to go into this equation. The first one is gravitational potential energy. And this really has to do with the height and weight that the object or system is at. So in this case, it is our sphere, and the gravitational potential energy can be measured by the equation m times g times h, which is just the weight of an object or system times the height at which it's at. So say we had an object with the mass, or a ball with let's go with an eraser with the mass 1 kilogram, and the g value is 9.8, of course, and the height is 5 meters. Yes, let's go with that. So the gravitational potential energy that would have would be multiplying all of those together. So 1 times 9.8 times 5 would give us 49 joules. So, yeah. Okay, so now to account for the spring potential energy. The equation that we use is 1/2 kx squared. And that might sound foreign, but K is our spring constant, which we just talked about, the stiffness, which represents the stiffness of the spring. And X is our compression distance of the spring. So let's say our spring constant is 10 Newton meters, and our compression distance is 2 meters. So when we plug that into the equation 1/2 kx squared, we're going to be squaring the compression distance, so 2 meters squared, multiplied by the spring constant, and multiplied that by 1/2, or divide by 2. And so the answer that we would get is 20 joules. So 20 joules is our value in our hypothetical situation of energy for the spring potential energy. So now we have accounted for the two forms of potential energy that are important in this equation. And now we need to account for kinetic energy, the initial kinetic energy. So that equation is 1/2 mv squared, where v is the initial velocity, because remember, we're doing all of this for the initial potential energy, the initial kinetic energy. And so let's say our initial velocity is 2 meters per second. And our mass, we already decided what our mass was earlier, and we said it was 1 kilogram. And that's all we need for that. So we take our velocity, we square it in 1/2 mv squared. We get 4, we multiply by that by our mass, which is 1 kilogram, and we take half of that. So we have 2 joules for our kinetic energy, our initial kinetic energy. So that is how you plug these numbers into our equations, and we would get that the total initial energy, how we do that is we add the kinetic energy, we add the gravitational potential energy, and we add the spring potential energy all together. So we get 2, which is our kinetic energy, initial kinetic energy, plus 20, which is our initial spring potential energy, plus 25, which is our gravitational potential energy. And we get that E initial is 47 joules. So now we have that number. And what we know about that number is that the energy, the final energy, will be equivalent to that number. And it can be in different quantities. So the kinetic energy doesn't have to stay at 2 joules. It can become 4 joules, but then we will lose some of that potential energy and end up with a final energy of 47 joules as well, because that's going back to the idea that energy is conserved. So now let's apply this equation, this long equation, or let me just state it one more time before we apply it to our experiment. So it's mgh1, the initial height, plus, or m times g times h1 is our potential gravitational energy, the initial potential gravitational energy, plus 1/2 mv squared, which is our initial kinetic energy, plus 1/2 kx squared, initial spring energy, equals mgh, final gravitational energy, potential energy, plus 1/2 mv squared, final kinetic energy, plus 1/2 kx squared, final spring potential energy. So that is our long equation. And so we're going to apply it to our scenario. So we're going to say, so I'm going to describe the equation that we're going to use for this experiment. So we're going to manipulate this long equation, mgh plus mv half mv squared, blah, 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 this long equation right here to fit into things that we can measure. So the initial mgh, the initial height is actually going to be 0 in our experiment. So that whole term, m times g times h, is going to go to 0 because anything times 0 is 0, right? Additionally, for our next thing, our initial kinetic energy, our velocity, our initial velocity, it's going to be at rest. So the initial velocity is also 0. And anything times 0, as we know, is 0. So that's going to translate to another 0. And then our 1/2 kx squared, well, first we're solving for k. We can measure the compression distances because, like we saw, there's C, A, B. Those are all the different compression distances, and we want to have that in our experiment and in our equation because that's going to be our independent variable. And then on the other side, mgh2, that's going to be the final height. That's going to be the height, the maximum height that the projectile, the sphere, reaches. So that is going to be a value, so we need to leave mgh in there. And mass is something we can measure, and we know g, and then we'll have to do h for the different trials. But then, so that's our gravitational potential energy. We're going to leave that in the equation. So right now we have the equation looking like 1/2 kx squared equals mgh. And then, let's think about our kinetic energy. Well, at the maximum height, the velocity of the object is 0. And that's a really important concept to understand. So at the maximum height, there's a split second where the velocity is 0. So that whole term, 1/2 mv squared, is going to go to 0 because 0 times anything is 0. So plus 0, and then plus our, sorry, there was a low battery sign, plus our spring potential energy. Well, when it's at Hmax, the maximum height, it's not going to be in contact with any spring. So the spring constant, the whole spring potential energy, is also 0. So the equation that we're left with is 1/2 kx squared equals mgh. And we need to manipulate that equation to by solving for k, because that's going to give us our spring constant. And we could plug it in later, but I think it would be nice to do the algebra and solve for k right now. So we have 1/2 kx squared equals mgh, and we're doing our best to get k alone. So the first thing that I would do is multiply by the reciprocal of 1/2 to get k, start by getting k by itself and cancel out that 1/2. So we would get 2 mgh equals kx squared, which is what I have written in the corner there. And then the next thing that we would do, as you can see, I did that, is divide by x squared. Yes, we would divide by x squared to get k on its own. So then our final equation for k will be 2 mgh over x squared. And we're going to leave it at that. So that is our expression for the spring constant k in terms of quantities that can be obtained from measurements made with equipment usually found in a school laboratory, which is what it asks for a part 2. Next, it asks, design an experimental procedure to test the hypothesis in which the student uses the launcher to launch the sphere. Assume equipment usually found in a school physics laboratory is available. So again, we can't just be like potential energy and kinetic energy. We have to use this expanded version and our spring constant equation. In the table below, it says, list the quantities and associated symbols that would be measured in your experiment. Also, list the equipment that would be used to measure each quantity. You do not need to fill in every row. If you need additional rows, you may add them to the space just below the table, blah, blah, blah. I don't need them. I'm only needing to measure 3 different quantities for each trial. So, and those quantities are going to correlate to the values in my spring constant equation. So the spring constant equation, let me repeat, is K equals 2 mgh over x squared. So first we need M. What is M? M stands for the mass of the projectile. So the mass of the sphere, the symbol is M, and the equipment we could use is a weighing scale. That's what I wrote. Next, we need to account for H, which stands for the height that the projectile reaches, so the maximum height. And the symbol is H, like I said. We can use a meter stick for this, so because that is something that we would find in a physics laboratory. The last quantity that we need to measure is the displacement of the spring when it is being compressed. We know that these values over here are A, B, and C, so we just need to know what those compression values are to plug them into our equation when we solve for them. And since that is going to be our independent variable of this experiment, it's the thing that we're going to be changing, the compression distances, that is an important part to measure, and we'll be using a meter stick or a ruler to measure that. Additionally, just to mention, so like I said, the compression distances is our independent variable for this experiment, and our dependent variable, what we're measuring, what is changing throughout, well, might be changing throughout each trial, is the height that the projectile reaches. Okay, so we're gonna move on to the next part. So the next question says, describe the overall procedure to be used to test the hypothesis that the spring constant of the spring inside the launcher has the same value for different compression distances, referring to the table. Provide enough detail so that another student could replicate the experiment, including any steps necessary to reduce experimental uncertainty. As needed, use the symbols defined in the table and/or include a simple diagram of the setup. So I did include a diagram, but let me just talk through what this experiment will look like. So there's going to be our launcher, and there's going to be a sphere. So the first thing that we'll do is measure the mass of the sphere and write that in for all 3 trials, because we can assume that the mass will be the same no matter what. So we're kind of gonna make a table, and we're gonna have trial 1, trial 2, and trial 3. Right? And for each of these trials, we need to measure M, X, and H. Just to review, M is the mass of the sphere, the projectile, X is the distance that it compresses, and H is the maximum height that it reaches. So M is just gonna be M throughout, right? X is our compression distances, so we're going to change this for each trial. So for the purposes of simplicity, it's given us A, B, and C as different compression distances. So those are the three that we're going to be using in the trial. So for our first trial, right, after measuring the mass on our weighing scale, we're going to take it, put it in the spring launcher, and we're going to move the spring launcher pin back to A. Then we are going, the spring launcher is going to be positioned vertically. I drew a pretty bad diagram right there, and that is our compression distance X. That is where H equals 0, and that change in H is our maximum height. So it's not going to be from the ground under the spring launcher. It's going to be from the top of the compression distance and the bottom of the sphere, essentially. That's going to be our H equals 0 value. It's kind of a reference point. So we use those a lot in physics. I probably should go over that really quickly. We can denote kind of any height to be our H equals 0. And then our delta H, which is the change in height, delta, it could also be denoted as delta X. The change in height is measured from that H equals 0 to whatever other distance we go at. So say our H equals 0 is right here, and I go 5 centimeters up, our delta H would be 5 centimeters. So that's just a quick demo on what it means to set a reference point of H equals 0. So going back, we know our reference point of H equals 0 is the top of the compression, the compressed spring, essentially. So we have our mass, we put it in the sphere, we moved it down to compression distance A, and then we measured that compression distance A with our meter stick, and then we put the meter stick up against a wall, use the spring launcher, and launch the sphere directly into the air. Then to reduce as much error as possible, I think it's important to use a camera to film the maximum height that the projectile reaches, because human error, we can't really see the perfect, meter stick measurement that this projectile is going to be reaching. So using a video, we can look back on that H value after the trial is finished. So sphere launches in the air, comes back down, we get it, we look at our video, we see what, as precise as we can be, we get that H measurement of what the max that the projectile reaches, maximum height that the projectile reaches is. And we also need to make sure that H equals 0, the bottom of the meter stick, is at the bottom of the compressed distance. So it would be best to have someone holding it or pinning against a wall or something like that. So that's our H for the first trial. Then in the next trial, we're going to keep the mass because we've already measured it, so we know what it is, keep it consistent. And then we're going to compress it, distance B. From there, we are going to measure the compression distance, so measure what B is and write that in our table of values. This is the trial table that I've been making. Obviously, I haven't actually been denoting values for A, B, M, but I'm writing it down to explain what goes where and when. And then I'm going to refer back to this table of values to calculate or to show how the calculations would be made for this experiment, so to solve for the spring constant. So we've measured our compression distance, we know our mass, we're gonna shoot the spring launcher in the air. Again, H equals 0, the meter stick must be at the top of the compressed spring. Then we use our video camera, we get a video of where the H max is for the projectile, and we look back at that after the trial's done, and we draw in, or we write in our H value. The video really just reduces error. There's no other explanation for it. And Next, we will do the last trial. So that means we have our M again. This time we do C as our compression distance, measure that with a meter stick, put our meter stick back up, put the sphere in the launcher, or well, the sphere is already gonna be in it, but the pin is gonna be set to C. We've measured that, we got our mass, we shoot it in the air, use our video, capture that maximum height. When we look back over it, we write in what our measured height is. So now we have 3 trials, each with different compression distances and the heights that we gathered as our experimental data. So the next question asks, describe how the experimental data could be analyzed to confirm or disconfirm the hypothesis that the spring constant of the spring inside the launcher has the same value for different compression distances. So for each trial, we have to take the measured values of mass, height, maximum height, and compression distance, and plug them into our equation, right? So if we refer back to our equation, we said K equals 2mgh over x squared, right? That's our equation right there. We know that G is 9.8 meters per second squared. That is the acceleration due to gravity, which is acting upon this projectile as it's in the air. So yeah, that's the G value. So that is going to be the same for all trials. Additionally, our mass is going to be the same for all trials, right? Mass equals M. But the H and the X values are going to change for each trial. So we have to plug them in separately with the mass and with mg, and we need to solve for K. And that would be the way that we confirm or disconfirm the hypothesis that whether the spring constant is has the same value for different compression distances. Now, it's important to remember that there will be experimental error. Even though we took the video to get the maximum height closer and took other precautions to get the height correctly by the reference point, there will be errors because this is a human experiment. So when proving the hypothesis, we need to be careful about just seeing whether the spring constant is the same. They might not be the exact same values, but if they are really close or really similar, that would be confirming the hypothesis as well in a physics 1 laboratory. I'm sure that in these high-tech places, it could be different, but that is important. And I just want to remind all of you that this K equation that I took was from our earlier part 2 over here. K equals 2mgh over x squared. And we got that from our equation that comes from the law of conservation of energy. So it's all stemming back to this law of conservation of energy. And that equation that we got it from is mgh plus 1/2 mv squared plus 1/2 kx squared equals mgh plus 1/2 mv squared plus 1/2 kx squared. And that is representative of the initial potential energy added to the initial kinetic energy, which is equivalent to the final potential energy plus the final kinetic energy. So that's just the total energy initial is equal to the total energy final. And that is the law. That's basically what this whole problem stems from. The reason that we're able to do this experiment is because of the law of conservation of energy and the way that it comes into play in our daily lives. So moving on to the last part, the question asks, another student uses the launcher to consecutively launch several spheres that have the same diameter but different masses, one after another. Each sphere is launched from position A. Consider each sphere's launch speed, which is the speed of the sphere at the instant it loses contact with the plate. On the axes below, sketch a graph of launch speed as a function of sphere mass. So I thought about this equation, or I thought about this problem, and I was like, well, in the beginning, it has spring potential energy. It has to, because it's on a spring, there's compression distance, there's going to be a spring constant, and the instant that it loses contact with the plate, it is going to have some form of kinetic energy, right? Because potential energy is the stored energy. So before it leaves the plate, the instant before it leaves, it has potential energy, but no kinetic energy, because it's stored potential energy. If we remember my definition, potential energy is stored energy that's based on the position or circumstance of the object or system. Kinetic energy is the energy of the object or system in motion. So as soon as it leaves that spring, it is going to be in motion. So there is going to be some kinetic energy. So we can say that we take our spring potential energy, we take our equation for that, which is 1/2 kx squared, and we set that equal to 1/2 mv squared. And essentially the mgh, the potential gravitational energy for the initial and the final. So yeah, the potential gravitational energy for the initial and the final is going to be essentially the same, because it's moving basically nothing. It's just the instant it loses contact with the plate. So we don't really have to account for that. We can kind of cancel them out on both sides, because they're going to be equivalent. And then we know that the initial velocity of when the sphere is standing still is going to be 0. So 1/2 mv squared, the initial kinetic energy, goes to 0. So that's 0 plus, and then we have our 1/2 kx squared, which we're going to leave. Then on the other side, at the final, it's not the final path of the object, it's just what we're deeming to be the final, which is the instant that it loses contact with the plate, is going to be 1/2 mv squared. As I said, mgh we don't have to account for, and then it has no more contact with the plate, so there's no spring constant, there's no spring potential energy anymore. So with that, we can solve for velocity in terms of mass, or mass in terms of velocity, because what it asks is, on the axes below, sketch a graph of launch speed as a function of sphere mass. So we need to know as the velocity increases, what happens to the mass? As the mass decreases, what happens to the velocity? So an equation is the best way to figure that out. So we have 1/2 kx squared equals 1/2 mv squared. And I'm going to solve for velocity in terms of mass. So the first thing that I do is I multiply by 2 on both sides, which cancels this 1/2. And then I divide by m to get m on the other side, and then I square root it all. So that leaves me, it's just some algebra, that leaves me with v equals square root of kx squared over m. And if we think about that equation, let's say we plug in that the mass is 1, and then the mass becomes 2, right? So that's the mass increasing. When the mass is 1, we can assume that all of this is constant. When the mass is 1, let's say all of this, kx squared, although it stays the same, is going to be equivalent to 1, right? That all goes to 1. So then it would be 1 over 1, and the square root of that is 1. So velocity equals 1, right? And then when mass is 2, that's the square root of 1/2, which is less than 1. So what that tells us is that as mass increases, velocity decreases. And so that's helpful in determining the direction of the direction of the slope on our graph. And so that's going to be decreasing slope, right? So then I drew this curve here because it's a square root function, right? So it's not going to be linear. It's not going to be a linear straight slope, but it is going to be continuously decreasing. And the sphere mass is never going to go into the negative values, and the launch speed is also never going to go into the negative values. So it's just getting closer and closer to zero as the mass increases, because we know that as the mass increases, the velocity decreases. So getting slower, closer to zero. And that is the last part of this FRQ. I hope that you guys have enjoyed listening to me talk about this FRQ for 45 minutes. And I hope you learned a little bit about energy and work and how to tackle this long FRQ. So thank you so much for listening. Have a great day.